Welcome to the third live interactive session on mechanical behavior of materials, part 1. Today we will discuss about the content that has been uploaded in week 3, and we will discuss about the assignment on those contents, and also we will discuss some concept related questions based on those concepts. So myself Vikas Tiwari, I am research scholar at Department of Material Science and Engineering at IIT Kanpur.
And hello, I am Rajneesh Pandey. I am also a research scholar at the Department of Materials Science and Engineering at IIT Kanpur. So let us begin the discussion for today from the assignment questions first. So this is the first problem given in the assignment for this week. So it says that a dog bone shaped AA6061 specimen, basically this is aluminium alloy specimen, was subjected to a load of 1 kilonewton under uniaxial tensile loading. The initial gauge length and diameter are 25 mm and 6 mm respectively. So we are asked to determine the true stress acting on the material if the final diameter is 5.5 mm. So let me draw the specimen first. So it will be somewhat like, basically a dog bone specimen is a cylindrical specimen. So it looks something like this. And this is the reduced section. This is the gauge length, L0. And diameter of this section is known as D0. So, and here force F has been applied, which is a tensile load of 1 kilonewton. F. So we are given with F is equal to 1 kilonewton or 10 to the power 3 Newton. L0 is 25 mm and D0 here is 6 mm. So we have seen in the lectures that true stress and true strain are related to engineering stress and engineering strain by the relations sigma is equal to S into 1 plus E, where sigma is the true stress, S is the engineering stress, E is the engineering strain. And for engineering true strain, we have ln 1 plus E. Also, here we shall assume or we assume that the volume remains constant. So if the volume remains constant, it means that the at any instant of time, the area A multiplied by length L will be constant. So it would be similar to the initial area multiplied by initial gauge length. If we substitute the values, okay, let me first write down the expression for engineering strain also. So it is nothing but the change in length divided by original length. So from here we can get the value of L. So we are here, final diameter D is also given. This is 5.5 mm. So let us substitute the values for a cylinder. This cross section would be circular, so area will be pi D square over 4. This multiplied by L. This will be pi D0 square by 4 multiplied by L0. So if we substitute the values, this pi and 4 would will cancel out from both sides. So we will get L is nothing but D0 square over D square multiplied by L0. And upon substitution, we get D0 was 6, so 6 square over D was 5.5, so 5.5 square multiplied by L0 was 25 mm. So we get this L as 29.75 mm. Now we have the value of L, so we can get this E, which comes out to be this sorry, what happened to this? Yes, here if we divide this, then we will get this L over L naught minus 1. So basically we need this value of 1 plus E. So I'm directly rearranging the equation to get 1 plus E. So here we shall get L by L naught, and after substitution we get 29.75 over 25. And now let us see the stress values and strain values of true stress and true strain. So sigma is given as S is the engineering stress, which is nothing but the force divided by initial area E naught. So this will come out to be F over E naught multiplied by 1 plus E. So upon substituting, we get 10 to power 3 over E naught is pi D naught square over 4 into 1 plus E. We have found 29.75 divided by 25. And if we substitute the values and calculate, we would get sigma is equal to nothing but 42.09 megapascal. So this is the value of true stress. So here the answer would be this one, 42.09. So let us move to the next question. This is also a numerical problem, a very simple problem, where the statement says that the true stress sigma versus true strain epsilon diagram for a strain hardening material is shown in the figure below. The material was loaded initially up to a point A, where the values of stress and strain are given. This is 500 megapascal and this is 0.5. And from there, it was unloaded to point B, where the values of stress and strain are 100 and this strain is unknown. Given that the Young's modulus of elasticity E is 200 GPa, the strain at point B is. So we are given with Young's modulus, and we know that Young's modulus is nothing but the slope of this line, of this elastic region, basically. So we are given the coordinates. If I write this value in the form of coordinates, then I will write it as 0.5, 500, and this will be epsilon, 100. So E is nothing but the slope of AB, and this is given as y2 minus y1 upon E2 minus E1. So it will come out to be 500 minus 100 divided by 0.5 minus E. So this. Now, if we substitute the value of elasticity, it is given as 200 GPa. 200 GPa, and in terms of MPa, this will come out to be 10 to power 3. So this is 400 divided by 0.5 minus E. So upon rearranging the equation, we will get this 0.5 minus epsilon is nothing but 2 into 10 to power minus 3, because this 200 will cancel out this 400 by 2 times, and this will become 10 to power minus 3. So again, this epsilon will come out to be 0.5 minus 0.002. So this comes out to be 0.498. So here the answer will be this. Now let us move to the next question. So here the statement says that which of the following represents the constitutive equation for a viscoelastic material based upon Maxwell model. So let us first draw the schematic of the Maxwell model. What a Maxwell model is, basically it is a model for viscoelasticity where spring element is attached with a dashboard element in series. So it will be like this. And here, see here, everything is given in terms of stress. In the lectures, it was discussed in terms of force. So let me write in terms of stress only. So here, sigma has been applied. And here we know that the total strain E would be nothing but here the spring constant is given as E. Dashboard constant has been given as N. Stress sigma has been applied, and sigma star and epsilon star, sorry, sigma dot and epsilon dot are the stress rate and strain rates respectively. So this total strain is nothing but the strain here due to the spring spring element plus sigma times the time, means that is the strain due to this dashboard element. In the class, these notations were used. They are nothing but Ke is represented as E here, and this Kv is given as N or eta here. So let me substitute these values here. This comes out to be epsilon is equal to sigma divided by E plus this sigma T divided by N. Let us rearrange this. So we would get, if I take this and this side, so it will come out to be N multiplied by E, and this will be N by E into sigma plus sigma T. Let me bring this T also on this side. So this will come out to be N into E over T, and this will be nothing but N over E multiplied by sigma over T plus sigma. And this strain divided by time and stress divided by time, these are nothing but the strain rate, and this is the stress rate itself. So this can be written as N E dot, sorry, yes, and actually I should have denoted it in terms of epsilon, but since the strains are small, we can consider that these are this engineering strain and true strain are equal. So this will be N E dot is equal to N upon E into sigma dot plus sigma, or in terms of true strain, we can write it as N E dot is nothing but N over E sigma dot plus sigma. So this is the relation. So here if we see, the option 1 is the correct option for this answer, for this question. So let us move to the next question, and Mr. Vikas will discuss this.
So in the fourth question, it is given that figure shows the white model for a viscoelastic material. Find the time required to reach a strain level of 0.999 of the terminal strain, which is represented as E infinite, that is at the time t equal to infinite. So given parameters are elastic modulus of the material, for especially here spring, for spring, and neta or n basically represent the dashpot constant, that is 10 megapascal, and initial stress is 10 megapascal. So first let's understand this arrangement, White's model arrangement. So this arrangement is basically consists of two components. First is a spring, this one is a spring, and this one is dashpot, which is nothing but a viscoelastic material. So, and these two components are connected to each other in parallel manner. So that's why the force that and it is fixed on one end, this one end, and in one end we are going to apply the stress, initial stress 10 megapascal. So in that case, if you see, as we have seen in the module lectures, and we have derived the formula, in this case, the force that will be resultant force that will be acting on this system will be nothing but is the will be the addition of both the stresses acting on separately on individual components. Just like on a spring component, if it is acting as Fe, and then in dashpot component, if it is acting as F V. So this will be, unique equation for this particular system. So on the basis of this equation, we have derived the relationship, and also the strain will be is nothing but will be equal in all the cases. Okay, so that's why we have proved the relation. E is nothing but E at time t. E is basically the strain developed in the system at time t, and E infinite is the strain that is developed in the material or the system at time infinite, t equal to infinite. And 1 minus E exponential to the power minus times t divided by tau. So this is the formula that we have derived in the module lectures. And based on this, we are going to find out the value of time after which the strain that is developed in the system will be 0.999 times of the terminal strain. So what we have given with, we have given with E at time t will is nothing but 0.999 times E infinite. And next thing that we are not knowing here in this formula is tau. Tau is nothing but is a time for relaxation. But and here the time that what is asking is we need to find out the time. Okay, so first we need to calculate tau, and we have seen that tau is nothing but 1 by tau. The relation is 1 by tau is equal to ke divided by kv, and k is nothing but the spring constant, elastic constant of spring. So it is nothing but E, and kv is for viscoelastic material. That's why it will be correspond to dashpot constant is n. So after substituting the values 100 megapascal divided by 10 megapascal, we will get the value of tau is nothing but 1 by 10. 1 by 10 is nothing but 0.1. So this is the time for relaxation. And now we have this formula, which is E equal to E infinite 1 minus exponential times minus e to the power minus t by tau. So we are all given with this all values. So we are just going to put all those values. E is nothing but 0.999 times E infinite, and this is E infinite, and this is 1 minus exponential minus t. Tau is nothing but 0.1. This one. So this E infinite will be cancelled out by this E infinite, and we will have E exponential. My 1 by 0.1 is nothing but minus 10 times t, and it will be equal to the 1 minus 0.999, and that will nothing but 0.001. So now now minus t minus 10 times t will be nothing but ln 0.001. So after calculating this, we will get 0.069 second. So it will becomes approximately 0.69 seconds. So for the option being fourth, okay, that will be correct for this case. So this will be the timing after which the strain in the system will have 0.999 times then terminal strain. So let's go to the next question. So this is the theoretical question. In this question, question is elastic limit is the point in the stress strain diagram. So basically this question will be understood with the help of stress strain diagram. So basically we need to know that what is elastic limit. So as it has been also discussed in the module, this is the typical stress strain curve for the ductile material. And if you see, there are three crucial points comes into this diagram. So one is proportionality limit, another one is elastic limit, and then we will get yield point. So, and in the question it is saying that about elastic limit, which statement is correct? So first statement is up to which the stress is proportional to strain. So basically, first I need to represent these points A, B, C. So C is nothing, A is nothing but proportionality limit up to which the stress is proportional to strain. So that's why first option is not correct. B is elastic limit, and elastic limit defines as up to which, if material is loaded and weak, and after removal of that load, if material again regain its shape and volume, then it is called elastic limit. So basically the correct definition in this whole statement in options will be up to which the load is removed, original volume and shapes are regained. So, and second statement, let's look into this. At which elongation takes place without application of load, this is incorrect. And third statement is correct. Up to which the load is removed, original volume and shapes are regained. And fourth option is material start deforming plastically. That is also incorrect because it's somewhat related to the yield point. So correct option is nothing but third statement. Now go to the sixth question. Which is the most important property used in the metal working process? So metal working process is nothing but these are the processes in which we do plastic deformation in order to get different shapes of product elements. So which property basically matters a lot in this case is nothing but toughness. So toughness is nothing but okay. I think there is query.
There is a query in the chat box.
Yes.
So Mr. Sanjit, he says that, but material will start deforming plastically. This is at 0.002 strain. You are absolutely correct, Mr. Yes. Sanjit. Actually,
actually, what you wanted to ask, Sanjit, na? So can you unmute yourself and ask the question, Sanjit?
Sir, actually in question number 5, you said that the option D is incorrect. So sir, like what's the logic why option D is incorrect?
Okay, let me come to this point. Material start deforming plastically means what? Let's understand with the example. Like if you have a sample, okay? So when you start doing deformation in tensile testing, then first, what are the events are going to be happen with this sample? Let's understand. So first, at point A, what happens? Up to point A, the material will follow the Hooke's law, basically, where the linearity is going to be followed. Means the stress is proportional to strain. And even after that, linearity is not going to be followed anymore. So in this region, linearity is not followed. But still, if you are going to unload the sample, so material is going to regain its original shape. Up to this, obviously it will regain, but after up to this point as well, it is going to be regain itself. That is elastic limit. But elastic limit, yes, it says that elastic limit means is the maximum limit of elasticity. But first plastic deformation, you should know it should start from yield point. At yield point, basically, you say that 0.2% basically strain we consider generally. This is the standard that has been made out in order to understand if the curve like this is a smooth curve of kind of thing. If we have, so how we are going to define the yield point? So first plastic deformation will always occurs at the yield point. You understand?
Basically, if you want to correlate with the elastic limit, so you should cross the elastic limit to get any amount of plastic deformation. That's why we take this 0.2% strain, so we can get some evidence of plastic deformation in the material.
But in case of, if you see in the case of like a low carbon steel, you will get this kind of curve. You have seen this. So here there are distinct 2 points where we can define the yield point, where first deformation, plastic deformation occurs. But in this case, basically, we cannot get this kind of, distinct point where we can differentiate that where yields, first yielding starts. So the 0.2% is kind of standard that has been made out by the, some particular agencies, which will define the after permanent 0.002% amount of permanent deformation shows the first yielding, and that is basically we are known as offset yielding.
So we hope we have clarified your doubt, Sanjit.
Sanjit?
Yes, sir. Yes, sir. Yes, sir.
Okay. Anybody, if you face any difficulty at any point, please raise your hand or put your question in the chat box so we can have a look over it. So let's move to the next question, sixth one.
Okay. In sixth one, which is the most important property used in the metalworking process? So in metalworking process, basically, we are going to deform the material and we want to make product out of it. So different shapes like sheet forming operations and even rolling, forging, etc. So in that sense, the most important parameter is toughness. Why is it toughness? Because toughness is nothing but combination of ductility and strength. So only strength you cannot make the criterion, or is the most important parameter as a to get the thing like a metalworking process is to the optimum level or not. Means if you are doing the metalworking process and if you are not knowing that what is the strength, and even along with if you are not knowing the ductility as well, so you cannot even possibly make a correct prediction about how much we are going to deform it. Because if you see stress strain curve, we will get the toughness as a stress strain curve, means the area under the curve, we will get this value. So it is not only about ductility, not about only ductility, that is basically can be understood by the elongation term, and not only strength that can define that how much you are going to deform the material in the metalworking process. So you need to have the idea about ductility as well as strength, then only you can perform the certain metalworking operation. So that's why toughness is most important parameters in metalworking process. So for the sixth questions, the toughness is correct answer. Now go to the seventh question.
So let us move to the next question, and this is a numerical problem. Let me discuss this problem. So here the stress strain behavior of a material has been shown, and we are asked to determine the toughness in the units of Newton meter per meter cube. This is nothing but joule per cubic meter. So you would have seen in the lectures that toughness is given as the area between area under this stress strain curve. So basically we need to find out this area, this entire area. That would give us the toughness. So it's a very simple question. Let me divide this entire region into three different shapes so that we can easily get the area. Let us term these points as A, B, C, D, E, and F. So the toughness would be nothing but the area under this curve. Stress strain curve. So how will we calculate the area? Firstly, we will take the area of this triangle ABF. So this is area of triangle ABF. Then we shall take the area of this rectangle BDEF. So this is area of BDEF plus the area of this upper triangle BCD. So area of triangle BCD. So if we take the values, what we will get is this is nothing but half into base into height, and base here is 0.004. So this is 0.004 multiplied by the height, and height here, see, you can take this value to close to 75 because it's obvious here, and roughly, since it is not given accurately, so you can approximate it to 70 also. So I will go with 75 for now. So 75 into, this was in megapascal, so we will multiply it by a factor of 10 to power 6 plus the area of this BDEF rectangle. So it is nothing but length into breadth. So length here would be 0.012 minus 0.004 multiplied by, this height is again 75. So it would be 75 into 10 to power 6 plus area of the upper triangle is half into its base. Its base is nothing but this 0.012 minus 0.004 multiplied by the height, and height here will be, since this is 75, so height will be nothing but 120 minus 75. Into 10 to power 6. So if we calculate this value, it comes out to be nothing but 93,000. So 9,30,000. Someone is trying to annotate here. Please do not do such things. If you want to ask anything, please raise your hand or put a message in the chat box. Even you can unmute yourself and ask the question. Okay, so it is nothing but Newton per meter square. Why is it Newton per meter square? Because this was given in terms of megapascal, and here strain is unitless. So it was nothing but megapascal means 10 to power 6 Pascal, which is nothing but 10 to power 6 Newton per meter square. We have already put the value 10 to power 6, so it comes in Newton per meter square, and it will roughly translate to 90 into 10 to power 4 Newton meter per meter cube. So here the answer will be 90 into 10 to power 4. So let us move to the next question. So here it is a theoretical question where it has been asked that which type of UTM will have easy amplification of forces. So it was clearly discussed in the lectures. The answer is straight away servo hydraulic. Why is it so? Because in screw driven or linear motor actuated or electromagnetic pistons, there will be some sort of transformation of energy, or there will be some work on the components itself. But in case of servo hydraulic, the pressures means pressure transfer will be there, and you would have seen like this, that this is transferred to this region. So there will be an easy amplification of the forces. So here the answer is servo hydraulic. Now let us see the next question also. So here a tensile test performed on universal testing machine measures. So let us discuss this question with Mr. Vikas. So sir, please.
So actually it is been asked that which fundamental property that we can derive from the stress strain curve, which we are going to get from the universal testing
Let us
machine.
see the options one by one.
So
So
basically true stress and true strain. So
we know that stress values cannot be directly measured.
Yes. Actually, first we need to discuss that what are the parameters that we get from UTS stress strain curve from that we obtain from UTS. So basically, UTS is a machine. UTM is a machine that basically gives two fundamental parameters, and it gives the curve between load, that is force, versus elongation, that is del L. Because these two parameters basically we are going to directly control and basically get from that UTM machine.
Yes, see, we have apparatus to measure the force, that is load cell, and we have an apparatus to measure the elongation, which is extensometer like or strain gauge like devices. So we can get these values directly.
So on the basis of these values, load versus elongation, we are going to get all the other values like true strain, true stress, engineering stress, and Young's modulus or Pajan's ratio. All other are going to be derived by this two fundamental property that we are going to get from the UTM machine, and that is load versus elongation. So this correct answer is fourth option.
Okay, so let us move to the next question.
Okay, so in this question, in a tensile testing of a known alloy, actually it is not visible. Why it is so?
This
Okay, because of this options. Okay, in a tensile testing of a known alloy, the elongation observed to be erroneously higher than the generally observed for the alloy. The possible cause of this basically error is what? So as discussed in the module as well, so what are the possible causes, and even what kind of safety and even the precautions you should take care of during the tensile testing. So because of that, we get the erroneously higher elongation during the tensile testing. So one possible reason is extensiometer was not used. Yes, because the extensiometer is the equipment that measures the elongation accurately. So extensiometer generally are put on the gauge section, gauge length, and on the 2 points, if you see, if it is your tensile sample, sorry, it is something
let us
like
consider
dog
the
bone.
gauge
Only gauge, no? So like that, dog bone shape. So in the gauge section, at the extreme ends, basically we are going to put the extensiometer in order to calculate accurate value of elongation of only in the gauge section.
So basically it excludes everything over this and below this point.
Yes.
Means at the starting of the gauge length and at the end of the gauge length only, it measures what is the change in the length or dimension. It ignores everything over and below it.
And Professor Sasang has also discussed in the module lecture that extension, when we are going to deform the tensile sample, there is also the deformation in the equipment material itself. That's why the material stiffness is also play an important role. So second option is material stiffness is very low. If material stiffness is very low, so certainly there is some amount of strain developed is going to be in the equipment material itself. So it will actually, it is not going to deform plastically, but at certain level in elastic regime, it is going to deform. So that's why stiffness also matters if extensiometer is not used there, because extensiometer includes only the elongation in gauge section domain. So now go to the third option, micro slip occurrence across the gripping end. Okay. So I think
let us first discuss the options, then we will take this question.
Okay. So micro slip is also maybe the reason, because if you are going to grip tensile specimen, if you are not going to grip this specimen properly at the crosshead ends, so definitely it is going to give some kind of elongation over there, and that is going to add up to your
Results finally.
Output elongation. So that's why we will end up with some wrong values. So that's why this also this options is also correct. Now fourth option is testing was carried out at slow strain rate. So basically whatever the this question is all about the testing point of view, means machine point of view. So in machine point of view, what are the errors that could be possible which is not which is not in our control. So basically testing was carried out at slow strain rate. It is in our control. We always put this fixed slow strain rate while doing the tensile testing. So that's why this option will be excluded, and that's why.
So answer to this question is first, second, and third options.
Yes. So this
let us mark this. Okay. So Sanjit, you are asking, when we do tensile testing using UTM, where is the extensiometer kept?
Yes, I just showed you.
Let us draw a clear schematic of the dog bone sample mounted on a UTM.
So suppose this is your sample, if dog bone shape.
Sanjit, have you ever done any tensile test using the UTM?
Sir, actually, like in my second year of undergraduate program, I saw that tensile testing.
Okay. So you have seen the specimen, right?
Yes, sir. This dog bone sample.
Okay.
So if you see the Sanjeet here,
Mhm.
so this is the dog bone shape of sample, and these are the two cross heads. Basically, I'm not sketching this
Yes, this is just a
schematically
schematic to means
because there
convey
is
to you.
also load cell here. Also, load cell is going to be situated here, and so basically these are all load frames. If you have seen in the module lectures, so around this all the load frames. So load frames is a part of machine, like a machine component part. So that's why here this is the our sample. So this is the gauge section basically. This
Yes.
point is the gauge section.
Right after the reduced part means from where the uniform length or uniform cross section begins, that part is considered to be the gauge section between the two extended parts means.
And we always concern about this particular part. Why you are not considering the shoulder part? Because why you are reducing this cross section in order to ensure the deformation, that is necking basically, and
Yes,
failure.
uniform deformation basically occurs in this gauge section only.
Gauge section only. So that's why we are only concerned about the elongation in that zone. If we are getting the elongation along the elongation of the material, like this one material of the equipment itself, then it will give you a wrong value. So that's why if you going to perform the tensile test, you are going to put this extensometer at this extreme end in the gauge section, so that we can accurate measurement for the accurate measurement of the elongation in the gauge section only.
So
this is
basically
the purpose.
these two pins of the extensometer, they basically move away or from their positions, and this is electronically sent to the computer system attached to the control system. So it monitors how much is this change, and it gives the elongation in terms of change of length.
Yes.
So here at the gauge section,
and that's why we have discussed that the fundamental parameter that is going to be measured by this equipment is elongation and force. So these two things that basically we get from this particular machine, and then we are going to plot this curve between the elongation versus force, and then we are going to derive all the other parameters from
so
that.
Sanjeet, hope this doubt got clarified.
Yes, sir. Yes, sir.
Okay, so let us see some more questions related to these concepts of week 3.
Okay, so let's go to the next question. Okay, this is the numerical problem. So let's solve this. During the tensile test of a steel sample with the initial diameter 12 mm and gauge length 50 mm, load versus elongation curve showed in the linear nature till 24 kilonewton. Yielding was observed at this load. At this load, the elongation was found to be 0.0518 mm. Determine the modulus of elasticity of the sample. So let's interpret those data in the form of curve, Stacey-Stein curve basically. So it is saying here, load versus elongation curve showed in the linear nature till to the this one amount of force. Again, we are going to interpret this where it is going to be linear. Up to what point is it going to be linear? There is a proportionality limit. So it is exists within the elastic regime. So if you see, the curve will be look like this. So up to this, the linear part exists, and that's why the slope of this linear part is nothing but the elastic modulus is going to be given. So
basically the shape of this curve and the shape of the engineering stress versus engineering strain curve will be exactly similar, because we are only dividing the values on y and x-axis by a constant value.
Yes.
So basically load by initial area gives the stress, and this elongation by original gauge length gives the strain.
Yes.
So let us go.
Given parameters, given values are what we have given with the initial diameter d0 is 12 mm and gauge length L0 is 50 mm. and load is given to corresponding to this point. Corresponding to this point in y-axis is nothing but 24 kilonewton. So we have to find out the slope of this curve, nothing but, and that would be equal to the elastic modulus of the.
Yes, basically slope after converting it in terms of stress and strain. Then we will get
Yes.
the slope as Young's modulus or modulus of elasticity.
So here we cannot directly take out the slope of this particular curve. We need to go to this curve. So we need not to plot this curve, but just to take the values. Because the always remember the slope in the elastic regime only in stress versus strain curve will give the value of elastic modulus. So in that curve, basically this slope will give the value of E. So we are going to calculate the slope with the help of these values, and is nothing but E by epsilon.
Yes.
So at this point, if consider the yield point, suppose if you are going to, what is happening? Okay. So first we are going to calculate this stress, that is F by A naught is nothing but 24 kilonewton divided by initial area is nothing but circular area.
Yes.
Yes.
Pi
So
d naught
because
square by 2.
D is given. So pi d naught is nothing but 12 mm. 12 mm square divided by. So it will be comes out what value?
212.21 megapascal.
212.2 megapascal. And you should remember, like 1 megapascal is equal to the 1 Newton per mm square.
So 10 to power 6 Newton per meter square.
10 to power 6. No, 1.
Yes, it's megapascal.
It's megapascal. No? So 1 megapascal is 1 Newton per
Yes,
mm
square.
mm square. So always when you see the mm, you should be happy like you are going to convert it directly Newton per mm square to directly
get megapascal values.
So no need to convert it into meter and all. So now the value of stress is this one, and value of strain will be del L by, sorry, this will be engineering strain. So L naught.
Yes, for this entire question, the values of engineering stress and strain should be used. Okay. So everything you consider by yourself that they are S and E.
Okay, so this value will comes out
1.036 into 10 to power minus 3.
10 to power minus 3 unitless. So now we can calculate the slope. It's nothing but sigma by E. Again, I have to correct here. So this value will be 212.2 megapascal divided by 1.036 into 10 to the power minus 3, and that will be comes out.
It will be around 205 gigapascals.
205 into 10 to the power 3 megapascal. So this will be the answer of this question. So first, the basic idea behind this question is you always need to keep in mind the elastic modulus of a material is always given by the stress versus strain curve, not load versus elongation curve. So you need to convert into elongation or force into stress and strain respectively. So go to the next question. So it is very interesting question, and I will explain this. Do all types of mechanical tests show necking phenomena? How can it be problematic in sense of tensile testing?
Okay, let us take an opinion from the audience first. If anybody wants to say something about this.
Ranjit, are you there?
Sanchit,
Yes.
And Manu. Anybody?
Sir,
Okay,
like
so-
during necking, sir, tensile instability occurs. So I think that only tension type of tests show the necking phenomena.
Yes,
you are right.
absolutely correct, Sanchit.
But in case of compression, why you are not expecting that necking will not occur?
Sir, because like in compression, sir, that barreling type of effect occurs.
Yes, bulging out basically. So yes, barreling type of effects occurs. But the first you need to know what is necking, and what kind of necking phenomena do not necking phenomena does not occur in all the mechanical testings, only encountered in tensile testings. The reason is, first we let understand what is necking. Necking is nothing but thinning of gauge section, gauge cross sections, thinning of gauge cross section. So at some point of time, you will see during the tensile testing, there will be some neck formation over there. So reason behind this, if you go to the microscopic level, so there will be material, there are a lot of irregularities in terms of defects, in terms of second phase particles, metallurgical defects like inclusions. So these are all basically inhomogeneities present in the material, and it's basically act as a stress reserves where the stress concentration around this particular location will be higher as compared to other part of the material. That's why when you are going to stretch this material, so relatively at a particular stress, which is we generally we know this particular stress is UTM. There are some points in the material where the local stresses are reached to up a very high value because of this stress concentration regions, and the cracks are developed over some particular locations, and that is going to be accumulated, and after some times you will get the failure. So this is basically necking, and this is necking, this kind of curve you will see, and after this UTS point you will see that in engineering stress and strain curve you will get this this will be downfall of this curve. Okay, so that is the reason. Necking is nothing but is only happening when you are going to stretch the material. When you are going to compress the material or other operation if you are going to perform, then this kind of phenomena is not going to be happen. As you Ranjit said that in compression is going to be barreling kind of shape. You will see. So this is the sample for the compression. If you are going to compress this, so after some time you will realize this kind of shape you are going to obtain. So this is called barreling. This is called barreling. So this kind of necking phenomena is not going to be happen there. Okay. So now second problem, second question is itself, how can it be problematic in sense of tensile testing? Okay. Why we are going to perform other tests apart from tensile test like compression test, torsion test, bending test? Reason is, in whatever the relation that we have found, derived till now, like for example, true strain is S times 1 plus E, epsilon equal to ln 1 plus E. So all these formulas are valid only for the uniform deformation. Means uniform deformation is up to this point, UTS point. This point, this is uniform deformation. These all points are valid up to this point. Beyond this point, you cannot apply those formula directly. Okay, you are going to be incorrect. So that's why this formula is not valid. So what happens when necking occurs? All the stresses acting after this UTS is going to be localized in narrower region. Is basically in that regions, and that's why there is no significant amount of elongation, but still there is a radial direction deformation is taking place. Means cross-sectional area is going to be decreasing much rapidly.
Yes, basically here the stress becomes very complex. It turns to the multi-axial stress system,
which is called triaxial state of stress. So initially we are assuming uniaxial direction, we are applying the loading condition, but after reaching to necking point, it is triaxial state of condition. That's why a lots of corrections are there, like Bridgman correction has been also discussed in the module lecture. So here all these formulas are not valid. Why it is not valid? Because uniform elongation is no more after this point. after this point of necking. So that's why uniform deformation is going to be restricted by this necking phenomena. That's why we are going, if we want to study stress strain behavior of a material at higher strength, so we cannot go simply by the tensile testing. So we need to develop higher strength by the other methods like torsion test, pure shear case, or compression test itself. So that is all about the concept about this questions. So go to the next question.
Okay, so let us see this question. Basically, this is a question which will help you to interpret the data we are getting from a tensile test. So basically here, consider the load versus elongation graph. This is a graph for a test which has been conducted in the UTM. So this axis is load in terms of kilonewton, in units of kilonewton, and here we get the elongation delta L in units of mm. So considering this diagram, we are also given the dimensions of sample. Basically diameter is given, so it would be a dog bone sample. Let me draw schematically. So here the gauge length is L0, and this diameter, as we discussed earlier, is T0. So we are given these values, and we have to determine the modulus of elasticity, yield strength at 0.2% offset strain, ultimate tensile strength, and uniform and total strengths. So let us go one by one. First, let me clear this area. Okay, so for the modulus of elasticity, we will have to restrict ourselves to the elastic regime or elastic part of this curve. Okay, so in the elastic part, what we will have to do, we'll have to take slope of this elastic line, this line in the elastic part. Slope will come out to be this. Not for this curve, we'll have to do it for the engineering stress strain curve, and the shape will be exactly similar to this, only the values will be in terms of stress and strain. So let me take 2 points. Here we can see that here the elastic behavior changes to plastic one. So let me take this point, and other will be this point. So for point 1, let me call this point 1, and this as point 2. For point 1, we have the value of force F1 as 5.5 kilonewton, as you can see from the graph. And elongation, I have already dropped a perpendicular here to get an approximate value from the curve. Actually, you can use graph papers or some softwares to get exact values from these scales. So this delta L1 comes out to be approximately 0.1.
Here our purpose is just to
yes,
tell about the concept behind that question.
Yes, so you can easily interpret the data if you get from some test. So at point 2, obviously the force value and strain elongation value both are 0. So this is 0 kilonewton, and delta L2 comes out to be 0 mm. This is the elongation, remember, not the length at any instant. With respect to the initial length, how much from the starting point it has been elongated over the time. So now we shall calculate the stress at these points. So S1 will be nothing but F1 by A0. I have already calculated, so I'll just put the values here. So it comes out to be 5.5 kilonewtons. So I'll take 10 to power 3 over pi d0, and let me put the value directly for d0. D0 is 4 mm, so 4 square over 4. So it comes out to be approximately 437.67 MPa. Remember, this is Newton per mm square, megapascals. And for S2, we'll have F2 over A0. So it will come out to be 0, obviously, 0 MPa, because F2 is 0. This is F2. Now let us see E1 and E2 also, so that we can get the Young's modulus. So E1 will come out to be delta L1 over L0, which is nothing but 0.1 over 20, which comes out to be 0.005. It is unitless because it is a strain value, and similarly E2 will come out to be delta L2 over L0, which is nothing but 0. So from these values of S1, S2, E1 and E2, you would have seen in the basic mathematics that slope of any line can be easily determined if 2 points are given which lie on that line. So slope of this stress strain curve in elastic regime will be nothing but E is equal to delta S over delta E, which is nothing but S1 minus S2 over E1 minus E2. And this comes out to be S1 was 437.67 minus 0 over this 0.005 minus 0, and it comes out approximately to be 88 GPa. So we get the Young's modulus as 88 GPa approximately. This is GPa. Okay, so we have calculated the first part. Now let us see the yield strength at 0.2% offset. So for 0.2% offset, this is the load versus elongation curve. If we would have if we were given with the engineering stress strain curve, then we would have directly put the offset line at 0.002 strain or 0.2% strain, and we would have got the yield strength. But here it is in terms of load and elongation, so we need to calculate it. So let us see how we go. So basically, let me move to the next slide. So strain at the offset value, let me call it as E of, will be 0.002 or 0.2%. So this is nothing but, this would be delta L at offset over L0, which is 0.002. And upon substituting the value of L0 and calculating, we get this L offset as 0.04 delta L. This is delta L offset 0.04 mm. Now we have the value of this delta L offset. Now we can draw a line parallel to this elastic regime line of the curve, and we can note the point where it intersects. So this, let me change the color for better identification. Let us keep this as this green one. So it would be around this 0.04 to here. It would go approximately. This is causing a little bit problem. So basically, it will intersect at this 6 kilonewton load approximately here. So what do we get from here? We get the value of force at offset value, offset line, which is nothing but 6 kilonewton. Now we have the value of force, so we can calculate the stress over that point, which will be nothing but the yield strength, and that will come out to be F offset over A0. And if we substitute the values, we will get 10 into, because it is in kilonewtons, so 10 into 10, 6 into 10 to power 3 over pi d0 square over 4. So pi into this 4 square over 4, and upon calculation it will come out to be approximately 477.46 MPa.
So basically, this offset value we have calculated by analytical method. The graphical method you can only calculate if you have accurate scale onto which you can calculate the 0.002 permanent strain, which is plastic strain. Then you can draw a line which is parallel to the elastic regime line, and wherever it intersects to the original curve in stress versus strain curve, then you will get that point. which is called offset tilt one.
Okay, so we have calculated this yield strength also. Now let us see how to get the ultimate tensile strength from this data. So ultimate tensile at UTS, this point will be maximum. And as I told earlier that the curve will have the exact similar shape. So in the engineering stress strain curve also, here the maximum point will occur at somewhere here. So let us take this value from here only. At the UTS, this load will be also the maximum load which occurs at UTS. So if we drop a perpendicular line, we will get the elongation as 1.6, and this load will come out to be approximately 7.5 kilonewton. So from the given curve, if we want to calculate the UTS, it will be nothing but the stress corresponding to this 7.5 kilonewton load. So UTS
will be simply divided by the area.
Yes, so UTS will be nothing but this F at UTS over A naught. So this will come out to be 7.5 into 10 to power 3 over this A naught is pi 4 square over 4, and upon calculation we get this value as 596.83 MPa. So by this we get the third part also solved. Okay, so let us see how to find the uniform and the total strains from this data. So this is the,
as I said earlier, that uniform deformation is taking place in sample up to the UTS only. After then you will get localized deformation. That's why you are not going to get uniform elongation over there. That's why in this question also we are going to calculate the strain up to UTS. That will be corresponding to uniform strain basically. And the total strain you can easily get from the plot as well up to this point.
Yes, so basically from here to here we will get, this is see, this is the elongation axis, but if we consider this diagram to be the stress strain diagram, then this would be the uniform section, and this will give us the total section. So to find the uniform strain, what we need to do, just simply drop a perpendicular line from the point of UTS on the elongation axis. This we get the elongation at UTS and divide this by the gauge length. So we will get the strain at UTS, which will be nothing but the uniform strain. So let me write it down here. So from the graph, after dropping the line, we get delta L at UTS, that is delta LU as 1.6 mm. So the uniform strain comes out to be nothing but delta U over L naught, which is 1.6 over L naught was 20. So this is approximately 0.08, or in terms of percentage, this is 8%. Similarly, from the graph, for total strain, we get delta LT. Let me call this as total elongation. So this we can see, if we drop a perpendicular line, it comes out to be 3.8 approximately. So this will be 3.8 mm. Therefore, total strain will come out to be delta LT over L0, which is 3.8 over 20, which is approximately 0.19 or 19%. So here we get these values. Okay, so these were some additional questions. Now, if you have any further query, please feel free to ask.
Sanjay, are you there?
Yes, Sanjay is the only participant right now.
So
if you have any doubt, you can freely ask that.
Sir, like we have this UTM for tensile testing. So, sir, like that, what machine is used for? Suppose we want to find out the shear strength.
Okay. Okay, so Sanjit, basically one full form of UTM is Universal Testing Machine. Universal Testing Machine. See, this is different from uniaxial testing machine. This universal testing machine, this machine has provisions for various types of tests. Actually, it is very similar to the uniaxial testing machine. It has this frame and everything is similar. But here, where the sample is mounted, there you have provisions for various mounting methods. So if you can elongate the sample by pulling this cross-head upward, then you can also compress it by pushing this downwards. So if we apply the pressure in this direction, compression test can be done. Now, suppose if you have a specimen and if you create some die like this, see, if you have a hole throughout this die, and if you place a sample here, and there is another die, sorry, this will be like this. So specimen is throughout these two dies, and if you press this one and pull this one, so basically you would put a shear stress at this specimen. So shear test can also be done. Similarly, there is a provision to press it down with the help of a spindle like this. And if you place a specimen, suppose a rod like this supported at these 2 points, then you can carry out the bending test also. So various types of tests can be conducted in this machine.
Actually,
So
Ranjit, you are asking about torsion test, no? Ranjit? Sanjit?
Yes, sir, means like like we have analytical formulas for calculating shear strength, but like in
Yes.
machine, how do we calculate it? So,
In machine, actually, we have discussed that in machine, suppose UTM machine, if we are using, then only we will get elongation and strain, elongation and force. So on the basis of that, you are going to calculate with some kind of software or and else. You are going to get you are not directly going to get the strain and stresses from the system itself.
see, Sanjit, if what shear strain is basically, you had
The shear strain, if you are talking about shear strain, so it is basically based on the torsion test. And torsion test basically is a separate tester where we can generate only pure shear case, and basically we rotate that sample,
yes, like you twist the cloths after washing.
Yes.
In a similar manner, a torsion is applied on the specimen.
So that is the different actually testing machine we are
Yes.
using for that.
That
is for
test
torsion
that test gives us the bending in terms of angle of bend,
Yes.
and that is converted to the shear strain further on.
Where no normal stresses are going to be applied, only the pure shear case, means only shear stresses are applied over there. So from that basically equipment, you are going to get the shear strain versus shear stress. There you are going to get some parameters. From there you can calculate this one.
okay,
Sanjit?
sir.
Okay.
Yes.
So for that you have separate, but for the compression test, for the tension test, even for bending test, you are going to use the UTM machine itself. That's why it is called universal, because multi-purpose. This machine is using for multi-purpose. Okay, Manu, are you there?
Yes, sir.
You have any doubt during the session? You haven't asked any question?
No doubt.
Okay, no doubt then. Fine.
So anytime if you face any difficulty, you just put that in the course portal. We'll have a look over it and we'll discuss in the
And please try to attend these interactive session, because without audience there is no interactive session. So we are just going to record this session and going to upload this session. It's just not the purpose of this session. It's just to interact with you people.
Please do come and discuss and encourage your friends also, if they are in this course, to come over here.
because we want to learn from you as well. If you will ask, we will prepare according to that, and we will come with more explanations in next session as well. So you can raise your question at the forum section as well, so that we can take up those questions from there, and we will come with the explanation in the next session.
Okay, so it was really a nice session as compared to the previous ones, because
Audience was there.
we did at least some interaction today. Okay, so thank you everyone for participating, and
Okay, thank you.
let us meet in the next session. Thank you. So we
Thank
are
you.
ending the session. Okay, thank you, Manu.